Hello and welcome back. This is now lecture 2. We're going to talk about variables, assignments, math, and strings, oh my. So let's get started. The first thing that I do want to talk about is errors, because we're going to make so many mistakes when we program, and sometimes the compiler tells us nice things, like exactly what went wrong. Other times we have to figure it out ourselves, which is unfortunate, but I'm going to teach you the tricks of the trade. So let's talk about the different kinds of errors that might happen when you're writing programs. So the first kind, the easiest kind, is a CompileTime error. So you're trying to compile your program, make machine code out of it, but you are speaking C++ incorrectly and the compiler is not happy with you, so it refuses to even compile your program. It's going to say, no, error, here is the line where something went wrong, fix that please. So something like, instead of saying int x equals 42, like int x equals 42, it would start to complain about that. That's a compile time error. You see the problem at compile time and the program doesn't even get to start. Okay, so let's do some stuff. Let's open up Visual Studio Code again. Back to where we were. It opens the same stuff, but I want to do this all in the terminal now. Make this nice and large for us. So I want to get to this folder. So I can say cd to go to it. So I'm right now in my home folder. I need to go inside of my Windows desktop, because that's the next thing right here, Windows desktop. And inside of that, I have my S21 code from class. Inside of that, I have CSCI 40. Inside of that, I have lec1, but I want to make a lec2 folder inside of CSCI 40. Okay? How in the world will I do that on the terminal? Well, I know how to do it on this thing, on the file browser. I can just right-click, go to, say, create folder. But no, we're going to do this on the terminal. And the command to do that is called makedir. Makedir, and then the name of the folder makes a new folder in your current working directory called that folder. Called folder name, whatever you want to call it. So I'm going to say makedir lec02. Bam, it's there. And I can say ls, but I think you saw it appear. So now it's there and it's empty. I can change directories into it, and now I'm ready. It's currently empty, but I'm ready to start writing code inside of it. Okay? One command you can do, now here it shows up, it's empty in Visual Studio Code. You can, there's one command that makes an empty file instead of an empty folder. It's called touch, like touch it and make it appear, like you're a magician. Okay, so touch errors.cpp. So now I've just made a file called errors.cpp, and let's start editing it. Okay, I also could have, of course, gone to File, New. But we want to be fancy, right? So let's get our boilerplate code back. Let's remember it all. Include iostream, so we can have cout, cin, etc. Endl, using namespace standard, so that we can use all the standard library code and not have to write standard colon in front of everything. And I'm writing a bunch of comments here, which is useful. Then we always have our main function. That's where our program starts. And the last thing that a main function should always do is return 0 to say that the program finished successfully. Okay, so let's make our compile time error now. Hopefully I can just copy and paste this. That would be nice. Yeah. So int x equals 42. You can see how it's not cool colored because there is an issue. If I save it, Visual Studio Code might even underline it for me if it thinks about it long enough. But at the moment it is not complaining. So we have to go to the compiler. Let's try and compile this. Remember what to do. It is G++. Standard equals C++ 17. We want the cool latest version of the language. Then you say the name of the file, errors.cpp. And then if you want it to be called something other than a.out, you say -o, and I'll usually give it the same name as the file, but without any extensions. Hit enter, and now you can see there's nothing there. It's just nothing got made for us, no errors file, just our original program. And it gives us the error message. Okay, so it says errors.cpp, then a colon. And the first number it gives is a line number, then a column number. So on line 7, column 5, there's a problem. int was not declared in the scope. Did you mean int? Ooh, how helpful. Yes, we did mean int. Okay, so that is a compile time error. And if you want to change that, then the program would compile. Okay, so that would cause a compile time error. And now on to a runtime error. So another thing that can go wrong is your program actually got to compile and it's running, but something bad happens during the execution of the program that cannot be recovered from. So the compiler wasn't smart enough to catch it, and it happened while the program was running. One thing that can go wrong is division by 0 for ints. So let's do this. Int x equals 42. That's all well and good. Let's try and get something. Let's try and change x. Cin x. And get a new number from the user. Enter a number, please. So send this text to the terminal, and then get this information from the terminal. These are going in two different directions, you see. So now, after this line, we have the x to use, to have and to hold. Let's divide 42 by 0 or something. Okay, so we'll see out, 42 again, divided by this new value of x. So if this happens to be a nice number, things are going to be okay. But if it's 0, we're going to hit a runtime error. Okay? And so obviously the compiler isn't smart enough to know what we're going to type. So that's why it lets it go. Okay, so errors exist. Now I can run it, /. And so let's enter a number like 2. And so it'll divide 42 by 2 because it sets x to 2. So 42 divided by x is just 42 divided by 2, and that works. If I rerun this program, 0. Oof, I get a very scary message. Floating point exception, core dumped. I didn't print any of that. Oh no. So that is a runtime error. Okay? So if you enter x, entering 0 here causes a runtime error. So the program was running, and an error happened that was unrecoverable. Okay? The final kind of error is the most subtle. The program compiles again, it runs, and it even finishes. It doesn't like stop halfway through with some kind of error message. A logic error is also known as a bug. You might have heard that term before. A bug is just when the result isn't what it should be. Even though the program works fine, you thought it was correct. So here's an example of a logic error, and I don't think I have to type this up for you to see what the problem is. So we'll set x to 42 here. It's like, oh yes, x, 42, totally. Make that box of memory, set it to 42, and then let's make a variable called x plus 1. Oh, that's an interesting name. I wonder what it should hold. And then let's set it to hold x plus 2. So it's going to hold 44. So this is a logic error because I think as a programmer you're probably expecting x plus 1 to hold 43, right? So that is the issue. And that is a bug if you really expected this to be 43 and not 44. Okay, so those are the kinds of errors that might exist in your programs. And I guess the rest of this entire class is to get you to solve them on your own. Okay? So now that we know about errors, let me fast forward a bit to what we're going to learn in at about the halfway point in this class. Okay, so I am going to show you something, and I don't expect you to understand a lot of it. Okay, I just want you to watch me speak C++. Okay, I took a Latin class my freshman year of undergrad at Fresno State with Dr. Chapman. She's wonderful. You should definitely take her classes if you go there. And what she did one day was she broke out our textbook and she just started reading Latin fluently, and we would listen. So that is something that is very nice when you're learning the language, because you can finally hear how it flows and how it's supposed to be used. And that's what I want to do to you right now, okay? Because I've been giving you these very simple programs, and I want to show you where we're going, okay? So just sit back, be a sponge, and pretend that you're learning your native language as like a child or something. So we're going to make a counting machine. I know, super exciting, but it's going to showcase a lot of cool things that we're going to learn later, all right? And I don't expect you to understand any of this. I really hope that you watch the rest of this, but feel free to fast forward if it's getting overwhelming, okay? I do not want to scare you off, but this is cool stuff. So we're going to make a counting machine, and I want to make my own type. Like, we have ints and stuff. I want to make my own type. I want to make a type called counter. I want to be able to make a counter. It's like, bam, it exists. Just like I could say int x, bam, it exists. I don't actually have to give it a value yet. We'll talk about that later. And I want to be able to do things like increment my counter. So a counter should be able to be incremented, or reset, incremented. Should be like a reset function, an inc function. I don't know. I think that's, or like a get count function to see what we clicked. So like maybe the number now is 18 because we pressed inc enough times. So that's what I want to be able to do. And I'm going to make this counter type work like that. Okay? Again, I don't expect you to understand any of this, but it's a very cool concept. Something like this. c.get count. Something like that. So I'm going to make this work. Okay, so just sit back, watch this happen. I'll call it counter.cpp. I'll include iostream, use namespace standard, and here's what I want to do in int main. I want to make my counter. I want to increment it a couple times, c.inc, c.inc, like I'm clicking it. I'm counting how many times I'm jump roping or something. And then I want to output c.get count and a new line. So I've clicked my counter 4 times, and I would like to have this print. What do you think? I think it should print 4. So it should reset itself when I begin. When I click it 4 times, it increments itself, and then finally I can extract whatever was in there and see what the count was. Maybe at the beginning, just to make it clear, I can reset it to 0. Okay, so I'm like performing operations on my C variable, which is interesting to think about. And this is where we're going in this class. Okay, it'll take us quite a few weeks to get there, but it's fun to think about. And so to make my own type, I'm going to say class counter. Don't worry about any of this. I have to put a semicolon there for no good reason. Public, let's see, private. Right now, let's keep it all public. Why not? Int count, I'm going to have a reset function. A reset function returns nothing but does something. It's going to take our count and set it to be 0. Whenever we click the reset button, it should set our count to be 0. It's like our counter has a piece of memory inside of it. It has its own little count. It's like, here's my C. It has its count inside of itself, set to 0. That's where we're headed. Same for inc. It doesn't return anything, but it does something to our counter. It's going to set the count to be 1 more. So whatever it was, plus 1. And then finally, get count finally gives us back the count. So it's int. It gives us back the integer, just like main gives us back a number as well. Int get count. It's going to give back to us, return, whatever our current count is. So it's keeping track of this thing inside our C, and we finally want it back, whatever it was now. So inc should make it 1, again should make it 2, etc. Okay, and so we'd like for it now, this last line, line 29, when it actually does something and prints something out, we want it to print out 4 because it's inked itself 4 times after being reset. Okay, so that is our first fancy example of a custom type. It's called a class, and we'll get there soon, okay? Or maybe in a while, depending on how good you feel about this concept. All right, so I'm going to compile and run this and show you it working, and hopefully it is interesting and excites you. All right, so let's just go back to this so I can change it up a bit so I don't have to type too much. /counter, and hey, we get 4 back. So eventually you're going to be able to make your own types and have operations on those things, on our C's, and they'll do whatever you want, do your bidding. Okay, so that's where we're headed, and I hope that was fun. You watched me speak some fancier C++. Okay, So let's go back down to the beginning again, where we are. Let's talk about variables, because I have not gone over them too much just yet, and you'll definitely be reading about them a bit more. Excuse me. But let's go in depth. Okay, so a variable, which might as well make that bold, is just something with a name, and you can have it hold a value. So like we've had our int x, of course. My favorite example, int x equals 42. It makes a box in memory called x that you can refer to later, so you don't have to type 42 anymore. Okay, and let's talk about how you can name a variable. So x is totally fine, of course, but valid names are the following. Your variable must start with an underscore, a lowercase character, or a capital character. Okay, it must start with these. Okay, after that you can use any more of those, but you can also use digits. So for example, foo is okay, hi mom, 42 is okay as a variable name, but like 2x is not an okay variable name because it starts with a number. It has to start with either an underscore or a lowercase letter or a capital letter. Okay? And you're going to see a lot in your programming career, people name their variables in different ways. There are two common patterns. One is called camel case, because it's like you're looking at the back of a camel, and every new word is a hump of the camel, because they capitalize it when it's a new word. So that's like a camel, like that. Or you can see people using lots of underscores when there's a new word in their variable names. Okay, those are the two common things. This is more C++ and Java. This is more Python-y. People have different conventions, of course. But it's up to you. You can decide whatever variable names you want. It is your program. Okay, that's a variable. Now let's talk a little bit more in detail about how they get made. Like we did talk about it a little bit, but let's go a bit further. So to declare a variable, you must specify its type. When you say int x equals 42, you make space. You declare to the C++ compiler that I would like room, please, for x in memory. Okay, this is called a declaration and initialization. All in one big line. Initialization. Okay, but if you wanted to, and I've hinted at this, showing you a couple examples, you don't have to say equals 42 immediately, especially if you're going to get this value from the user. There's no use. Int x by itself, and just int x by itself makes room in memory for something called x. Okay, it makes room in memory for something called x, but doesn't give it, or it doesn't specify a value. We're going to talk about what it holds in a second. Don't look ahead at the next slide preview. So this is called a declaration only. Whereas this makes room for x. This one makes room for x and also sets it to 42. Okay, those are your two options. We'll talk about those a bit more. So if you just say int x semicolon, what in the world do you think x is? What goes here? If I just say I want room for x, please, it's like please make room for one int, please. That's what you're asking the compiler. What goes here? What gets set to x when you just declare it but don't initialize it? And the answer is garbage. It holds absolute garbage, random memory values, not zero, not anything nice. It is random, whatever was in memory at the time, because that's extra effort to set it. We don't want to waste CPU cycles. So it holds absolute garbage, and let me prove that to you. So I don't know what I want to call this. I don't know, undeclared variable, undefined, uninitialized. Let's call it uninit.cpp. How about that? So let's take some of that, take some of that, return 0, of course. There we go. Now, whatever shall we do? Let's say int x, int y, int z, int p, int q, int r. I think that's enough to cause the problem. Sometimes if you just declare 1, it actually gets set to 0 and it's nice to you. But this should ruin things. In theory. I can always add more. 3, 4, 5, 6 of them. So let's do this. Let's print x, print y, print z, then p, then q, then r. Okay, cool. Let's try this. So g++, standard equals C++ 17, uninit.cpp-o, uninit, made the file, compiled, uninit. So none of these things have values. None of these variables have values. They're declared, but they're not initialized. I should say it here. That's the word, initialized. Cool. All right, so here are the problems. It looks like Q and R. We were lucky with those. But the rest, look at the random values that they held. Okay? This one's actually nice. This one's close to a power of 2. The rest of these look odd. Okay. So that is the story. That is the moral. Always initialize your variables. There are 2 ways that you can do it. Okay? Well, 3 if you count using cin or something. You can, say int x, some time passes, eventually you give it a value. Okay? You can just say it on a line by itself, x equals 42. You don't have to say int again because we already know that it exists. This makes it, this just sets it. Okay? Slash resets it. Or you can declare and initialize like we've been doing. You can say int x equals 42. I guess you do have the third option. Secret third option, use cin. You can declare the x and then say cnx. That's another way to put it. Secret option 3. That's also possible. Okay. So just make sure to always do that. Before you use the variable, it better be initialized, otherwise weird things will happen. I should write that. Before you use a variable, make sure it's initialized. Otherwise, weird things happen. And there's a technical term for weird things. It's called undefined behavior. And we'll see more of that as the class progresses. Bold. There we go. Let's not overwrite these things. And I'm sure it wants a comma there. Okay. On we go. Okay. How do we set variables? So we have used the equal sign so far. We've noticed this. You can say a equals b or initialize it with the type as well. Int x equals 42, x equals 43 if you want. But there's more to it, okay? That equals sign, it's called an assignment statement. So here is assignment.cpp. X equals 42, this is an assignment statement. This sets x to be 42. We can also set x to be 43. Okay? And now x is 43. So that's really unfortunate. Because I just did this in my program. If I print them both, I used the same variable for different values. If you're a mathematician, that should make you shiver. Because I said, okay, x is 42. Oh wait, never mind, x is 43 now. Okay? So this is an assignment statement. We just did that. And equals in math, if you remember how that works, equals in math just means that a variable has a value, and that value never changes. Like, I don't know, x equals square root of 42, whatever that is. It doesn't make sense in math to say, oh yeah, x is now equal to pi. No, because these two aren't the same anymore. It's not true. In C++, variable values can change, and just watch out for that. Don't expect it to be a value because it might have changed. Okay, so how in the world do these assignment statements work, you might ask? Because you can do cool things with them. I can do the following. X equals x plus 1. Question mark, exclamation point, question mark. And this is what happens. X is now 44. It's one more than it was. What? So the reason this works is you read assignment statements and they get executed from right to left. The right-hand side goes first. Okay? Happens first. And then there's always only one variable on the left-hand side because you store it into X. And then store it into here. So do the right side, put it in the left side. Okay? That's essentially what's happening. Do B, put it in A. Okay, there's a shorthand for this. There is x plus equals 1. That's one shorthand. Also x equals x plus 1. Or I should say that, shorthand 4. And there's also an even faster way to do it. To add 1 to a number, because that's a very common thing to do in programming, you can say x plus plus. Also plus plus x works, and you'll read about that in your book. So also shorthand for x equals x plus 1. So that's fun. So now what should x be? Take a guess. Now it's 46. Cool, huh? So now you know why it's called C++. It's one more than C, the next language. All right. So yeah, just keep in mind that things aren't what they seem, as evidenced by this little block here. Right-hand side happens before the left-hand side, so it would have been nice if we called it like the arrow operator. And some languages do that. They like put a colon here to make it look kind of like an arrow, but we're kind of stuck with equality. That's sad. Okay, so just keep that in mind, and let's see where we're going. I think we're doing well on time. Okay. So, I have not talked too much about all the fancy number stuff you can do, and we will definitely get there, don't worry. Let's talk about it a little bit more, because I did some math with you, but not a lot. Let's talk about how all this stuff works together. Go away, there we go. So values, or literals, those are synonyms, those are basic elements of a type. So the different kinds of values depends on the type, of course. So if we go back to the cloud again, the int cloud holds its values, okay? It holds 42, negative 42, 0, 1, 2, 12, all those things, on and on forever. But you can have things that become ints but aren't immediately ints, which is odd to think about, okay? So values in int land are like 0, 42, negative 1. Those are the basic elements of the type. That is, C++ doesn't have to work any harder to go from 42 to an int. It's already there. It's already at an int. Okay, it knows exactly what value to put in the box. Whereas an expression is any combination of literals and operators. Okay, so operators are the new thing now, like plus, minus, left shift, things like that. Those are all operators, and they require work to get down to a value. So for example, here is an expression, 2 plus 3 times x divided by 7 minus 1, whatever x was to make it 42. That's the expression, but like you say something like int z equals this. This is not what's getting stored in the box, right? It's not like, okay, yeah, z holds 2 plus 3 plus blah, blah, blah. No, that's not a value. Boxes hold values. They have to get evaluated. There's an evaluation process. We get down to 42, and that's the int. That's what gets stored into z. Okay? That's the main difference. I want you to understand the difference between an expression, which has work that's yet to be done, and a value, which is ready to be a member of the type that it belongs to. So this is immediately an int. There's no extra work that needs to get done. Okay? Those are a lot of new terms, but they're useful to know. And now you know them. Okay, so that's intland. We've been talking about intland. Let's continue for an interesting story about integers. So remember that integers can only store whole numbers, so no decimal places allowed. What in the world's going to happen when we try to divide things? Because division usually causes some decimal places to appear, right? So division on ints, it's still it's the slash operator. That's what you use in C++ to get division, like you say x divided by y, like that. Int z equals x divided by y, something like that. But it works a bit odd, okay? Doubles, it does exactly what you think it does, okay? It creates decimal places because doubles can hold those. Whereas on an int, you don't have room to fit decimal places. We'll understand what that means later. But ints can only hold those whole numbers, and so we need to understand what's going to happen if we try and put like 5.5. How do we shove that into an int? What do we do? And what happens in C++ is the decimals get dropped. Okay, there's no rounding that happens. They just get dropped. So it becomes 5. Okay, in this case. So no matter what the number is, I don't know, 42.134. If you try and put this in an int, x becomes, what is it? I feel like we're in Dora the Explorer, but yes, you totally probably just got it right. It's 42, yeah? So it's going to hold just 42. And let me prove this to you. Dun, dun, dun. So, how do I want to say this? This is integer division is the property that we are discovering. I'll call it division.c++. So here's int x equals, I don't know, 7. 7's a prime number. You can't divide it by anything and expect a whole number back other than 1. Okay, so let's say cout 7 divided by 2. And this is integer division. The decimals get dropped. So whereas in real life, I'm saying whereas too much, I find. In real life, you're going to divide, it's going to get 3.5, right? But in C++, with ints, you're stuck with 3. It drops the 0.5, okay? That's integer division for you, okay? Just remember it. It will bite you in the future. I can promise that. It's hard to learn, but you're eventually going to be burned by it so many times that you can't forget it anymore. It's ingrained in your mind, okay? I can promise that. Okay. Doubles do what you expect, okay? So, but only when there's 2 doubles, or at least 1 double. You would like decimal places sometimes, but you won't always get them unless you do something special, okay? So double division, that's the counterpart to integer division. Double division depends on the types involved in the slash, okay? Not, and this is key, not the type of the variable that's being assigned to, which is really odd to think about. So here's what I would like to show you. So double d equals x divided by 2. This has room to store the 0.5. But it's only getting the 3. What? What is going on? The issue is it's the slash. The slash itself wants a double. It doesn't matter what's being assigned to, that it holds enough room. No, it's the division itself. In order for you to get double division, one of these sides must be an int, or what must be a double. One of these must be a double to get double division. It doesn't care that you're about to assign it to something that is a double. It's going to drop them anyway unless one of these sides is a double. Okay? So, that's unfortunate. But now we know. Okay? So still integer division, because both x and 2 are ints. Let's do it here now. D equals x divided by 2.0. See the main difference? 2.0, that's a double. Forgot my semicolon. 2.0 is a double. And now one side of the division, one side of the slash, is a double, and so it'll make it properly, it'll properly do double division. Okay, so this will finally become 3.5. Bam. Okay? That's quite nice. That's exactly what we want. Now we have it. Double is also known as a floating point type. So this just means that the decimal point can float around in space. You can have very large numbers, like 2.5 times 10 to the 42. This decimal point can go wherever it needs to go to make large numbers like this. So it's also called floating point, and don't be scared when you see that. Okay, what if we didn't want to type 2.0? What if we had an x and a y and they were both ints, but we wanted a double at the end of the day? Okay, so maybe I had int y equals 2, and I wanted to do d equals x over y. Again, this is going to do int division, integer division, because life is sad. This seems hopeless because these are variables. Like x, we can't make a double out of an int variable. We can't make a double out of an int variable, can we? We actually can, which is weird to think about. But you can use something called static cast. Okay, you say static cast to turn something into another type. So we say static cast, and then the type we want to convert to. Between these two less than and greater than signs, angle brackets, then a parenthesis, then the variable to convert. And this will become, it will turn this variable, whatever it was, into the type that you want, assuming that's possible. For doubles, it's totally easy. Okay, so we can say static cast to get around this problem. Okay, are you ready? As long as one side is a double, we're cool. So let's make the x a double. Static cast, we want a double out of x. Double x divided by y. Turns x into a double for double division, to force it to happen. Yay. Okay, so that's how we can solve this problem. If we have two ints and we need to make one of them a double so that we can finally actually get double division. Okay. Finally, let's talk about printing doubles. Okay? I've printed them. They look nice. You can actually tell that they're not ints anymore. Like this D, I printed it out. It just says 3, whereas we know it's a double. There's the whereas again, coming back. We would like to show maybe 3.0, something like that, to hint to us that it's a double. Maybe that's something that we want in our program, and you can do that. Okay, so one thing I need to include is iomanip, and this is for set precision. Okay, something called set precision. IOStream gives us something called fixed already. And these are variables, in a sense, that you can give to cout to control how doubles are printed. It's very odd. It's best displayed with an example. So let me show you this. Double F, okay, or E or something. 3.14. I'm going to cout it. And it's going to cout 3.14. That's fine. I can control how it gets printed, though. I can say fixed, and I can say set precision to 7. And these are little variables that you can give to cout. It doesn't actually print anything, but it controls how the next double is going to get printed. They control how doubles are printed. So take a guess at what might get printed now. What does the 7 mean? Ooh, 1, 2, 3, 4, 5, 6, 7. 7 decimals of precision. Hey, so fixed forces it to show the decimal place. Or actually, it forces it to always be in not scientific notation. It tries to do that with larger numbers. And then set precision forces Cout to use 7 decimal digits. So you can use it to round, actually. So you can say Cout. Fix is already in there. We can say set precision instead now to, I don't know, 1. And now let's print F. So we're actually going to not get the 4 anymore because it's going to round it. 3.1. Interesting, huh? To 1 decimal digit. Okay, so that's just weird ways to control doubles and printing them out. Let's continue. Okay, chars and strings now. These are the character-based type. So we've been talking about numbers and division. All the other operators work exactly as you would expect. Like this is multiplication. It always works. It does the right thing. If it creates a double, there's decimals. If it doesn't, it creates an int, and there are no decimals. Plus and minus work as you would expect. There are some more that we'll talk about later, but that's enough for now. Chars and strings now. Let's get started. So this is odd to think about, but every character is really a number. Okay, so like I don't know, when I say Cout the capital letter A, this character, yes, it displays to me as A, but really deep down in memory, it's just a number, and the computer's looking up what picture to draw when it's trying to print out a character. It knows that it's a character, and it needs to print a non-number. So it looks up its number form as a character, if that makes sense. There's just a big long list of taking characters to numbers that a bunch of people in the 60s got together and decided. Okay, and this thing is called the ASCII table. That's how you pronounce it, ASCII. Okay, that is the ordering of the characters. It's really fun to think about. So let's discover what number is the character A. Well, we can do that. Chars_strings.cpp. I'm going to eventually use strings, so I'm going to say include the string library for the string type, using namespace standard, int main, return 0, of course. Okay, let us see what in the world the A goes to. So Cout, not A anymore, because this will just print A. Let me prove that to you. It prints the A. Okay. What's its number, though? Static cast. Hey, it's a number. It should be able to convert. Cast the A, please, to an int. What is it? A is 65. That's the number for A, in case you were wondering. Static cast int character A. Okay, so that is the number in the ASCII table that corresponds to A. So A maps to 65. And they actually go in order, so B maps to 66, which is nice. Let's look at the table now. Here it is. It's just Wikipedia. So here's the ASCII table. I encourage you to read about it. There are some non-printable characters. You want to look in this dec line. It stands for decimal. It's the decimal number. The rest of these are different number types that we'll talk about later in the class. So here is the new line. It is character number 10, in case you were wondering. And then the rest of these are odder ones that don't get printed. These are the printable characters. So starting at number 32, that's the space character. Okay? And if we scroll on down, then come the numbers after some punctuation. I can make this even bigger for you, actually. And then here comes A. It's number 65. Everybody agrees on these. And then we have the entirety of the capital alphabet with some more things after that. Then an @ sign. Or no, this is a backspace. I think we probably used the latest one. And then at 97 comes the lowercase characters with some more things, and then we're done. So that's fun to think about. That is how numbers are arranged. Odd, huh? That's the ASCII table. So A is 65, B is 66, space, what was that, 32? How fun. Okay, those are characters and they're just numbers, now we know. Okay, let's do fancier things with strings now. So, when you have strings, you can inspect them. So you don't have to just say, okay, I have my string S equals, and remember the double quotes for strings. Hi mom, semicolon, of course. These are individual characters. Surely we can talk to them, do something with them. And that is quite possible. So, you can use s.@I to get the ith index of a string, okay? So I'm going to use hello as an example. In memory, this is what this string s looks like, okay? And then we'll talk about what the @ does. So s looks like this, and it's made of a bunch of little characters, right? It's got the H character first, then the E, then the L, then another L, then the O. And these are all together. They're kind of separate, though. And so, you can say s.@I to get the ith index of a string s, the ith character. Okay, we say indices instead. So, cout s.at, it's like, this is a special library function. It works on strings. On the string s, go to, it's like operating on s, go to the location at 1. Okay? So it's going to print a character of s. Which one do you think this one will print? What is the 1th character, the first character? What is it? Place your bets. It was I. Did you get that right? And the reasoning behind that is that in computer science, you will remember this forever now, numbers, all indices, they all start at 0. 0, 1, 2, 3, 4. So if you wanted the H, you had to go to location, to index 0 in the string s. Okay? This is actually the 2nd character. To us silly mortals, but to the computer, it's the 1th character, let's say. And this is the 1st character. Okay? There it is. And so you can also manipulate these. How do I want to do this? We'll do that on the next slide, I think. So yeah, just get it ingrained in your mind that the indices start at 0. You can go up to 4 because there's, at least for this string, because there's 4 characters. For hi mom, how many characters are there? There are 1, 2, 3, 4, 5, 6. So the indices should go through 0, 1, 2, 3, 4, 5, and 5. So if you try to get the 6th index, which doesn't exist, what in the world's going to happen? Aha! you get a runtime error. You went too far. Okay, so the language it's watching its back. Okay, finally, I think this will be the last thing that we talk about today, capitalizing a lowercase string. So you can actually update things. So for example, I can change s.at0 to be the lowercase h. That's totally fine. Now if I see out s, it's no longer capital Hi Mom, it's going to be lowercase because I changed the first index, the first character in the string, to a lowercase h. Oops, I need to comment this out before I'm allowed to see what happens. There it goes. See that? It used to be capital H, now it's lowercase. We would like to, in general, take a string and make it capital. We don't know what the string is. There is a trick to do this. So for this string I can totally do, let's make a new string. String s2 equals blah. I'd like to capitalize s2, make capital blah. It's very easy, obviously, to do s.at0 equals capital B and call it a day. But what if I didn't know what s2 was? What if I got it from the user? If I did this, cin, remember that cin gets a value from the user and puts it in a variable. Ooh, what's going to happen now? Get s2, get a string from the user and put it in s2. That's what this does, cin. Remember the arrows go the other way to take data from like the keyboard and shove it into this way into s2. So now after this line, s2 holds a random string that we don't get to control as a programmer. Whatever shall we do? How can we capitalize it? If we knew that they typed a word, how can we do it? We can take advantage of this table. We know, remember this, that these lowercase letters come after the capital letters. So all we need to do is subtract the difference between a, lowercase a, and the capital A, okay? In one direction. I forget which direction. We'll figure that out together. But that's all we need to do to capitalize any string or any character, any alphabetic character. All we have to do to it is say C equals whatever it was plus some offset into the ASCII table, okay? Let's figure out what it needs to be. So assuming that it is lowercase, a lowercase character is what I should have said. Assuming it was lowercase, that's a big assumption, but let's assume. This is our first real problem that we're solving. We don't know what the string is. We want to capitalize its first character. We can do it. We just need to offset by the distance between the lowercase characters and the capital characters. So let's assume we had lowercase a. We need to bring it down to 41. So we need to subtract the to 65. We need to bring it from 97 to 65. So what's the difference there? We need to subtract that difference. And you can do the math if you want, or you can remember that these are all numbers still, and you can actually do math on characters. So if I just had 65, and I subtracted from that 97, I'd have my offset, right? I believe, because I then have a negative value. If I did the smaller number minus the larger number, that'll give me a negative number, right? Because I want to offset. I want to bring this lowercase a down in the table, okay? So this is the distance between the capitals and the lowercase characters. It's always the same. That's the same for B, minus b, because they're all right after each other. I believe this might work. Otherwise, I got it backwards. So let's try it. This should be the answer. So whatever the string was, s2.@0, we want to capitalize it. Let's make it whatever it was minus this offset. Plus this offset, excuse me. Which is going to be a negative number. Which is a minus a. Okay? Offset by the distance between the capitals and lowercase characters. Let's see if that does it. And these are the tiny little problem-solving skills. This is a difficult one at your current level, I can imagine. But with enough examples, you will be at this level, I promise. Okay? And it's waiting for me to input something I probably should have asked, but it's just waiting here. And I can give it any character I want, any string I want, blah, and it works. It offsets that b by this distance. It always is going to work if you give me a capital letter, or a lowercase letter. I can say hi mom again, it'll capitalize the hi. Sorry, it only takes the first string. When you get a string from the user, it only gets the first word. You can say, I don't know, Lawton. It's always going to work until you give it a weird thing. Like if it's already capitalized, then it's going to go by the offset, and it's going to go to a weird spot. So now that becomes a comma. But it usually works, and it works if it's a lowercase character, always. Okay? So that is this fun little example. So I hope that was enjoyable, and this is where I want to stop. Okay? Next time we'll pick up and talk more about types and how much stuff you can put in them. We'll talk about like the sizes of things, like ints and bytes and things. But that's enough for now. So I will see you in your lab. Yeah, see you then.